Okay, welcome to the last unit, which is two variable statistics. We're going to start off with 3.1, scatter plots and linear correlation. It's stuff that you should already know from grade 9 and also the introductory correlation assignment we did way back in February. So the end of the lesson will be a little bit mathy, but the beginning is not mathy at all. So by now you should know what an independent variable is. A variable that affects the values of another variable. Sometimes it's not obvious which one is independent and which one is dependent, but sometimes you can tell. For example, if you have time is, nobody can control time. So if time is one of your variables, typically time is the independent variable. The one that is dependent is obviously the dependent variable. It's on the y-axis. You know about scatter plots is when you have two variables and you plot it as a scatter plot. We've done that before. And you can determine if there's a relationship between the two variables by plotting the scatter plot and seeing if there's any linear correlation. In the next couple of lessons, we'll look at stuff that's not linear. It doesn't have to be linear. The relationship doesn't have to be linear. What kind of examples would be examples where it's not linear? What type of relationship is not linear? There's a lot of them. This is where we miss Krishna here. So, give me a mathematical relationship that's not linear. Ooh, nobody there. Okay, quadratic is nonlinear. Exponential is nonlinear. Cubic is nonlinear. All these relationships exist, and we just cannot assume that the relationship is always going to be a linear relationship. That's probably the most common one, but we're going to look at the linear and non-linear relationships in this section when we do scatter plots. Okay, so we've done this before. What would be an example of a positive, let's start with this box over here, a positive perfect correlation? What does that look like?
All the data points are on the line of best fit.
Yeah, you have a bunch of points, and if you and which way does it? No, I've already drawn it. We say positive represents a positive slope, so that would be a positive perfect. If you draw a line of best fit, all the points are on the line. A negative perfect would be the same thing like this. All on a straight line. What would be, I'm going to skip these for now. What would be a no correlation?
No points?
Well, yeah, you have a whole bunch of points, but there is no...
You can't have a line of best fit?
It's not obvious how you draw a line. So basically you have points all over the place. Like it would be anyone's guess as to what the pattern... There's no pattern. Like looks like there's no relationship between X and Y. Remember, the word correlation means relationship, right? Here, there's definitely a relationship. Like as X increases, Y increases. As X increases, Y decreases. Here, as X increases, who knows what Y does? Anyway, if you could copy this into your notes, that would be awesome. Or we can just... I'll post it. Maybe you just do this at a later time. Just fill it in at a later time. Is that okay?
Yeah.
Okay. So this will be in the notes. You guys can do this. It'll take you a few minutes. I don't want to pause the video for you guys to catch up. So you can do that later. All right. Let's go to the back side. That was fast. Did 1 out of 4 pages already. Look at that. On the back side, we want to come up. You know how we did that correlation assignment? We came up with an R value and an R squared value?
Yeah.
Okay. So the R squared value is something called the coefficient of determination. And it tells you how strong the relationship is. R squared is just the R value squared, right? It's just this number here is this number squared. So the whole point is, how do you get this correlation coefficient? Like how does your calculator determine that? So we're going to do it manually today. It's a lot of work to do it manually, even if you only have like 6 or 7 points. So generally speaking, people do not do this manually. They always use statistical calculators or spreadsheets or something like that. But we're going to just learn the math behind it today to calculate this number and this number. before you calculate these two things, you have to, in the formula, you have to find something called covariance first. And what is covariance? It's the mean, the average, of the products of the deviations. So you have a deviation for, remember, a deviation is just how far is a value away from the mean. That's what a deviation is. So you have, it's the product of the deviations, because we have two variables. We have an x variable and a y variable, and for each, remember, it's a point. So a point has two values, an x and a y. So for each point, you're calculating the deviation of the x coordinate of the point and the deviation of the y coordinate of the point. You're multiplying them together, and this symbol here means sum. So we're adding all these individual deviations of x and y together and dividing it by n minus 1 to come up with something called the covariance, which is basically like a combined standard deviation of x and y together. Remember how we calculated standard deviation of just x and, of one variable? Well, this is kind of a standard deviation of x and y together. How do you calculate r? It's just this number that we calculated up here, the covariance divided by the individual standard deviations. S stands for standard deviation of the x values times the standard deviation of the y values in the denominator. So we're going to go through an example of this. And if you do this, if you look at, there's a this number r will always be between -1 and +1. Why is it going to negatives? Because this numerator up here, the covariance, can be negative. Let's just show you why. So here's an example, a perfect negative relationship, perfect correlation. So all the points would be on a negative. So why is the covariance, this SXY, negative? Well, it's basically, it's the sum of all the deviations of x and y. So I just made up some values here. And let's say the values were 0.60, 51, 42, and so on. So the average, the mean for all the x's would be 3. The mean for all the y's would also be 3 of this very simple, set of data. So if you look at this point here, 3, 3, this is not the x value. This is just shorthand. This is the deviations for the x is 0. So this point here, x equals 3 and y equals 3, and they both represent the mean, so there's no deviation for x and y. Here, x is 2, but the mean for x is 3, so the x deviation would be negative, but the y value is 4, but the mean of the y value is 3, so this y value is 1 above the mean. So, but if you multiply these two together, in fact, if you multiply all these together, well, except for that, you're going to get a negative quantity. So this shows you that when you multiply the deviations for x and y, you will get negatives if you have a slope going down to the right, and you'll get a positive covariance if you have a slope going up to the right. So the numbers will be between -1 and 1. If it's 0, there's no correlation mathematically. If it's 1/3, it's between 0 and 1/3, or 0.33, it's weak. Between 1/3 and 2/3, it's moderate. And if it's strong, it's above 2/3 and 1. When we did the assignment in early February, when it gave you the line of best fit, it didn't tell you the r value, it told you the r squared value. So obviously r squared, whenever you square something, you're only going to get a positive number. So it's just basically the square of the numbers above it. And they, if you square 0.33, you get 0.11. If you square 0.67, you get 0.44. So looking at the r squared value, a weak correlation would be 0 to 0.11, moderate would be 0.1 to 0.44, strong would be 0.44 to 1. And that's how you did your assignment in early February. We can use both of these variables, r and r squared, when we're talking about linear correlation, but when we're talking about exponential or quadratic or cubic correlations, we're only going to be talking about r squared. We're not going to be talking about r. R's can only be used for linear correlations. Okay, so that's all the definitions I want to get to, summarized all on one page for you, and hopefully that's what I want to do now is get an example where we use these formulas. Okay. Sorry, that's probably enough of me talking. So let's do some math. Okay. I think the next one is this. All right. And we're going to do an analysis, and we're going to do it on an analysis of only like 6 data points. Typically, you would not try to find a relationship with only 6 data points. It's way too few to do a proper analytical analysis. You need many more points because it's just too few to be accurate. Let's say you did this. The reason it's so few is it allows us to do it manually. All right. So let's look at the example. A farmer assembled the following sample data for his last 6 crops. He's recorded the temperature, I guess the mean temperature during the season, I guess. I'm not exactly, it's not during the day, it would be for the whole season. And it would be calculated the yield in whatever crop he's growing in tons per hectare. And so, and there's a relationship between the temperature and the yield. So using a graphing calculator, create a scatter plot of the data. Well, let's just do it now. So 1.6. Can everyone just plot this in real time? So the temperature of 4. This is x. This is y. Temperature of 4. 1.6 would be about there. 8 and 2.4. 8, 2.4 would be about there. 10 and 2. 10 and 2. 9 and 2.6. 11 and 2.1. I don't know, about there maybe. 6 and 2.2. Let's put some scale here. This is temperature, degrees Celsius. This is yield in tons per hectare. Okay, very simple scatter plot. What would you calculate? What would you, if you're going to eyeball it and compare it to what we have over here, what do you think it is? This obviously has a lot more dots, but what would that represent, you think?
I think it's...
You think it's what?
Wheat, maybe?
Yeah, well, we don't really know. It's mathematically we were going to determine it, but what you say weak what? Weak positive, weak negative? Is the slope going to be up? If you draw a line of best fit, is it going to be up or is it going to be down? It looks like it's going to be up, right? I would say it's probably up, going to be up like that. Right? So it should be positive and positive, weak, positive, moderate. So let's say should be positive, weak. I guess you could put the word weak first. Weak, positive. Yeah, that'd probably make more sense. Positive, weak, or positive, moderate. Again, you can put the words in a different order. I think I wrote it the other way before. Yeah. All right. It's probably going to be one of those two. So if you graph it, like something like this, I just plotted it, with Excel. The reason I plotted with Excel is, what can Excel do for you? What did we do before when you're... it can tell you what? You guys did it for me in February. So what did you add? What did we call it?
I think you can find the mean, median, and mode.
You could, of each variable. Like here's your x's and here's your y's, but we don't really care about that. You just clicked one thing, and you clicked one thing, and it determined the line, right? Remember you did that? You determined the line? And what do you call this line?
Yeah.
What do we call it? Line of
Line of
best
best
fit.
fit.
What did Excel call it, or the Google Sheets call it? I think they called it a trend line, right? Trend line or line of best fit. And you could ask it to find the trend line. We're going to be doing this manually, believe it or not, but even though nobody would ever do it manually because it's way too much work. But we're going to add a trend line, and then you could ask it to do what? After you find the trend line, you want it to display the equation, right, of the trend line, and then it gave you the equation, and then you could ask it to display the r squared value. There was no option to display the r value, but just the r squared value, right? So that's what you ask Excel to do, or Google Sheets, or Desmos, or whatever. And for this example, you have that. Okay, so that's what the computer comes up with for the equation of the line of best fit, or the trend line, and the r squared value. So let's just write that down. So for using Excel, the r squared value equals and this has a name. The r squared value is called the coefficient of determination. The r squared value equals what the heck was it? 0.218. But it says determine the coefficient of determination, which is not the r squared value. So what do we have to do? So we have to take the square root, right? Because and the square root gives you two possible answers, right? A positive and negative. We are going to be looking for the which version are we looking for? The positive.
The positive?
Yeah, we're gonna. It's definitely sloping positive, right? So we're gonna take the positive answer. So if you do that, you get an r value of 0.467, and we're gonna take the positive branch. Take positive because slopes upwards. Oh, sorry. Okay, so therefore, what is it? Is it positive weak or positive moderate? Or sorry, weak positive or moderate positive? If you use your scale, the r value, well, both the r squared value. Let's just go use the r. So the r is plus 0.467, so that would be between 0.33 and 0.67. So it's going to be. This confirms it's a moderate. Therefore, it's a moderate positive correlation. Okay, that was easy. If Excel does it for you. If you do it yourself, it's not so easy. We're going to do it anyway, okay? Can I flip the page? Let me know when I can flip the page.
Yep, all good.
Yeah.
Okay, all good. All right. So, all right. The next page is hopefully printed out for you properly. Should be something like this. So this is the same data. This is only the 6 points we just had before. Let's just copy down the points. It was 4. If you take my word for it, it was 4 and 1.6, and then 8 and 2.4, and then 10 and 2.0, 9 and 2.6, 11 and 2.1, 6 and 2.2. Okay, those are the values. And the question says, let's find the correlation coefficient manually. And I wrote down that there's going to be 4 steps. The last one being the answer, finding r. So we're going to put that down here. What are the first steps you have to do? So if you look at the formula for r, it's this. So it has 3 parts. That you have to find this, this, and this, right? But to find this, you have to find the covariance. The covariance is this. So what do we have to find first in the formula? So we have to find the mean. So find x bar and y bar, which is find the mean of. And the reason we're using x bar and y bar instead of the other symbol is that it's a sample. Okay. All right. So if you know the mean, we can calculate this whole thing. If you know this and this, we can calculate the covariance. But what's the next step we would have to use? So that's just the numerator. We still have to know the denominator, right? So we have to calculate this and this, right? Step 2 would be to find Sx, which is the standard deviation of x, and Sy, which is a standard deviation for y. So find Sx, and again, S stands for standard deviation. And then once we have this, we can calculate. Once we have the means, we can calculate this, the covariance. So I guess you can do 2 and 3 in reverse order. It doesn't really matter. So this is basically the standard deviation of both x and y together. And lastly, we find r. All right. How do you find step 1? How do you find the means of both x and y? What do you have to do? So to find the mean, all you
Add
have
them together and divide.
Okay, so let's use this column to add them together. If you add them all together, do you want to take my word for it? It's 48. And if I add all these together, it's 12.9. So x bar is going to be the sum of all the x's divided by n equals sum of all the x's is 48. And n is 1, 2, 3, 4, 5, 6. There's 6 values. And that equals 8. And y bar, y mean is just sum of all the y's divided by n. And it's going to be 12.9 divided by 6 again. That equals 2.15. Okay, we've done step 1. Step 2 requires more space than 3, so I'm going to put 2 down here, and I'm going to put 3 up there. When you printed it out, did it print out the numbers in the little boxes?
No.
No. Okay, so put 2 down here. I also checked out how it prints. I don't think it printed this word total, so if you want to write the word total there, that's good too. All right, so let's do 2. We want to find the standard deviations for x and the standard deviation for y. Do you guys remember what the standard deviation formula is? From yesterday?
Nope.
Anybody want to find yesterday's notes and tell me what the formula for standard deviation is? Any brave soul? Should I go in?
It was x minus the u over 2.
Yeah. Okay. X. We're not going to. We won't use mu. We'll use x bar for the mean. Okay. And then.
Yeah.
And then. It's
over n.
But the way I've worded this thing is that we're going to assume that this is a sample. So it's not a population; it's a sample of the data. So the numerator, there's one for mu, like the symbol the sigma, but this is not, which is the population standard deviation. But this is a sample standard deviation. So it's not n, it's n. You remember what it is for a sample? It's opposed to
n minus 1.
It's n minus 1. Okay. And what are we going to do with all these things? This is an individual deviation. But there's lots of these points, right? Each point, each value has a deviation from the mean. So we're going to sum them together. And then what's the last step?
Yeah.
What's that? We have to square root the whole thing. Okay, so that's going to equal. Well, we don't have that yet. We haven't calculated the sum of the x deviations. So here's the x deviations. Right? If you find the x deviations and then calculate the sum, this box here would be the numerator there. So let's do that. So how do you find the deviation here? What do we have to do? What's the calculation for this point, this x value? How far does it deviate from the mean? Well,
4 minus 8.
it's 4 minus 8, right? So equals 4 minus 8, right? And that equals minus 4. I'm not going to do the math for each one, but so this one would be 8 minus 8, right? That's going to be 0. 10 minus 8 is plus 2. 9 minus 8 is plus 1. 11 minus 8 is 3. And 6 minus 8 is minus 2. What happens if we add all these deviations together? What do we get?
Zero.
It has to equal 0, so we don't really care about that, but it has to equal 0. Okay, so sorry. Oh, it's not. We're not using this. We forgot something. Sorry, I apologize. It's not. We can't just use this.
X minus x squared
Square. Yeah, we forgot the square. Sorry. I was hoping somebody would tell me that. All right. So obviously we can't use just.
Sure, I did, but everyone ignored me.
Sure, I was trying.
Well, if you write letters and if you post text, I can't see them, right? So you just have to be verbal about it. Yeah, it's squared. It's because summing all the deviations by definition will add to 0. So this is going to be useless. We have to do x minus the standard. This is the x deviation, but we don't use that. We use x deviation squared, and then we're summing all this. So it's not this column. I apologize. It's this column. This column is just this column squared, right? So this is going to be equals. I'm just going to do the first one, minus 4 squared. So that equals 16. This is going to be 0 squared, which is 0. 2 squared, which is 4. 1 squared is 1. 3 squared is 9. Minus 2 squared is 4. What's the sum of all that? Somebody want to add that up for me? It's not going to be 0 for sure. It's all
34.
34. Okay, so we don't use this number. We use that number. So it's going to be the square root of adding all these things up. It's 34 over. Since it's a sample, we're going to use n minus 1 over 5. And that is going to equal 2.608. Does it have units? The standard
No.
standard deviations? What are we measuring on the x-axis? We're measuring temperature, right? So the mean is going to be in degrees Celsius. The standard deviation is always, it's a measure of spread. It's going to be in the same units. So standard deviations have units. So this is going to be degrees Celsius. All right. So the standard deviation is how spread out is it? And again, it's a number that you calculate. It's just a number. That comes out to be a measure of spread of 2.6 degrees Celsius. Let's do the same thing for the y's.
Wait, sir.
Yeah.
I have a question.
Sure.
Why is it divided by 5, not 6?
Because we're doing, I said it was a sample, and a sample is, remember that formula? Let me get yesterday's notes. Hold on. Bear with me. See if I can find it. Where is it? What? Come on. I don't have that much notes, do I? Oh, here. Right, in yesterday's notes, if it was a population, we'll use the letter sigma. If it's a sample, we'll use the letter S.
Oh, I see it.
Yeah, and we're doing n minus 1. So it's just when you have a small set of data, if you know it's a sample, we use this. Okay, it's just by definition. Okay. All right, so.
Okay, thank you, sir.
No problem. So we're going to do the same thing for the y. It's going to be the sum of all the y deviations squared, not just y deviations, over n minus 1. So let's calculate this column. let's calculate this column over here. To calculate this column, you need this column first. So, all right. So the first one, the first value is 1.6. How far away is that from the mean? The mean is 2.15, right? So it's going to be 1.6 minus 2.15, and that equals minus 0.55, I think, right? Okay, I'm only going to do the formula for the first one, so we're just doing a subtraction of this versus that. If you do the other ones, should I just write the numbers down, or you want to do it yourself? Let's just write
it down.
Just write it down. So basically, it's going to be 2.4 minus 2.15, which is going to be plus 2.5. 2.0 minus 2.15 is going to be minus 0.15. 2.6 minus 2.15 is going to be 0.45. 2.1 minus 2.15 is going to be minus 0.05. 2.2 minus 2.15 is going to be plus 0.05. Again, if you add them all up, by definition it has to equal 0, but we're not really interested in that anyway. What we are interested in is this thing squared. So let's square all those numbers. This is going to be minus 0.55 squared, and that is 0.3025. I'm just going to write all the other answers here, so just copy them down. 0.0625. This is going to be 0.0225. 0.45 is 0.2025. This is, this is going to be 0.0025, and this is going to be 0.0025 as well. All right, so let's save some time. Let's just add these up. If you add them all up, you get 0.595. All right, so that's the sum of the square of the y deviations. Right, so that's the numerator here. So that's going to be the square root of 0.595 over 5, because it's a sample, it's n minus 1. And that's going to be 0.345. And does this have units? Well, obviously, if this had units, this has units. So what's the units for y?
Yeah.
It was yield, right? So
Yield?
Yield. No, that's the variable, but the units are tons per hectare. So how many tons of crop? We don't know what the crop is. Could be wheat, could be corn, who knows? But how many tons per hectare you get? Okay, so this was easy. This was a little bit more involved. Let's find this now. So find the covariance. This is covariance. And once we find the covariance, we can use this. So covariance is equals SXY, covariance. Let's write down the formula. What the heck was the formula somewhere? Let's write down this formula. Right? So that's going to be the sum of the individual x deviations times the individual, times the y deviations all over n minus 1. That's the formula for it. All right. So, well, we don't know what this stuff is. We have, basically, it's x deviations times the y deviations, which is going to be this column. Here are the individual x deviations. Here's the individual y deviations. So we have to multiply these two numbers together to get an individual product of an x and y deviation. And then we have to sum all those up to get this number. That's the number we put there. So this is just 6 points. It's taking us a lot of work just to do 6 points. But would you do this normally? No, nobody in their right mind would do this. Would you just use a calculator? But this is what your calculator does. All right. So this times this. So this is going to be equals minus 4 times minus 0.55. That's going to equal 2.2. Okay, so doing the rest, this times this, well, 0 times anything is 0. 2 times that is, I can do that one in my head. Well, this one's easy, I can do that one in my head. This is also pretty easy. Well, these are all easy. Yeah, we don't even need calculators. Minus 0.1. All right, now we just, so this is the product of the individual x and y deviations multiplied together. You get a product, and then we have to sum the product. So adding all those up, you get, you want to just take my word for it? Is that okay? Okay, I sense a yes. Okay, the answer is 2.1. All right, so now the sum of all this is going to equal 2.1 over 5. Again, n equals 6, right? So if n equals 6, therefore n minus 1 is 5. All right, and that equals 0.42. So the covariance is 0.42. I don't really want to attach too much of a number to that, but what it actually means, but just it's part of the calculation. So lastly, find R. R is this guy. Covariance divided by the product of the individual standard deviations. So R equals covariance divided by Sx times Sy, standard deviation x times standard deviation y, equals 0.42 divided by 2.608, standard deviation y, 0.345, and that equals a number. Does anybody want to punch that in? Well, what should it equal? Remember, what did Excel tell us it was going to be? Remember, Excel said the R squared value was 0.218, and then we calculated the R to be the square root of that, which is 0.467. Right? Do we get 0.467?
Yeah.
Okay. Yay, it works. So now we know that it's based on this, we know it's a positive, moderate correlation, which is what we, so therefore, manually, we confirm that it's a positive moderate. And hopefully that's the last time we ever do that, because that's a lot of work, and it's only 6 points. Imagine if it was 100 points. There's no way you would do that. But that's the calculation that's involved. So describe the relationship between mean temperatures and yields. What would you say? So you fill in the blank. As the mean temperature increases, what happens to the crop yield?
It increases.
Crop yield also increases. Now, just because there's a correlation, what can you say that A causes B?
No.
No, it's very hard to prove that A causes B. It could be that might not be the mean temperature. Maybe when it's cooler, if there's more rain, and it's the rain that causes the crops to grow less or something. Maybe it floods the fields or whatever. So even though we know there's a relationship, we cannot say, and we'll talk about that more when we talk about cause and effect, but it's very difficult to prove, right? However, we have to be careful. We cannot say that warmer temperatures definitely cause greater yields. we can say we can only say there's a correlation. It's hard. It's very hard to prove something, prove that A causes B. There's a saying in statistics. I'm going to start at the first part of it. You tell me what the last word is. Correlation is not. What do they always say when talking about statistics? Does anybody know the word? Correlation is not. Kind of rhymes with correlation.
Causation.
Causation. Have you heard that before?
No.
Okay. All right. Just because there's a relationship between the variables doesn't mean that one variable causes the other variable. It's hard to prove, and we'll get more into that later. Anyway, that's it. I'm going to call it. Let's see what the actual time was. Stop it. 40 minutes. No. How is that possible?